Okay, so we understand that how a composite video signal looks like, and and this is the typical composite video signals that produced from a NTSC perspectives. So, or we can say this is that how a one line scan looks like, right? Okay, so now let's say we encounter some more issue here. So see the vertical, when we do the vertical retracing, the one thing said that we did, horizontal retracing, that we understand that after, one line is scanning, we, go back to the next line. And for that we need, horizontal retrace, right? So, and the horizontal retrace, takes some time. But when we finish a, one frame or one field, then we need to go back to the beginning of a frame or a field, right? So that we call vertical retrace. Now for vertical retrace we also need some time, right? So that's why what we can say. So definitely when we do the vertical retracing, that we come here and then we go back to even in the beginning. So for that particular times, so definitely our camera should be on neutral. So at that times our camera should not scan any point. If it scans some garbage, some other kind of points will be coming. So you know so ultimately what we are doing is we are kind of losing some time. We are kind of losing some lines. In fact, ability to scan some more lines, we are losing that ability, right? So, or you can say that vertical retracing, you know at the times while the camera goes off mode or silent mode, while this vertical retrace happens and vertical synchronization happens, at the times is equivalent to 20 lines scan you know at the beginning of each field, right? So that means what? When it starts scanning, let's say it finishes, come to here after one field, and then it goes back to here. So during that times we can say roughly 20 line scan time passed. So, or in other words, we can say that from every field we basically lose the ability of scanning 20 lines from every field. So and for even field or odd field, both has 20 lines and 20 lines. If we lost the some sort of this kind of things, then total 40 lines we actually lose, right? 40 lines. 20 lines for 20 lines for, let's say, one frame, one field, for one field, and 20 lines for another field, another field, because a frame has two fields. So that means 40 lines, 40 lines we actually 40 lines, less 40 less 40 lines we can actually scan. Total how many lines? 525 lines, right? So but we cannot scan, we can't scan 525 lines. Rather now we have 525 minus 40 lines. So this kind of ability we have. So that means it is roughly, we can say, 485 lines, right? 485 lines. So 485 lines, lines we can scan if we consider this vertical retracing stuff. Okay. And how about this area? This, what is this area? This area, you see, this is for horizontal retrace and sync, right? So these are, we understand that how many lines we can scan. We can scan 485 lines, but how many pixel in one line, how many pixels we have, that is we don't know. Actually, it depends on the video format. It depends on you might have 300 lines or 240 line or 240 pixels or 300 pixels or 1000 pixels, right? It depends on that what kind of video formats you have. But at least we understand that, if from here to here, if this is our active, area, active line, then we can roughly say that, let's say total we have this much of time for one line scanning. But for horizontal retracing, we need to, reserve some space. So this is roughly 1/6 of the raster area. This number of right, we have to keep blank. So this from here to here, from this space to this space, or from this time to this time rather, our video camera will be blank. So this is mostly for synchronization and horizontal retracing. So ultimately these are, vertical retracing, and this is space. All these are your image data. And experiments suggest that, that we have, these sorts of image that we understand, right? So this is our object or area to be, taken the video. So, and let's say we just scan this line, and the immediate line is, let's say, this line we scan, right? So but in the real, what happens, maybe we can imagine infinite number of lines, right? And we don't know that in the real, scenario, when we are taking the video, we don't know exactly that which line is, more, important than, compared to other lines. So roughly we saw that, in between, lines in between that we don't scan sometimes, is more important. And is roughly suggest that around 30%, line we actually miss, that whose lines are basically much more, influential, much more important, in an object or scene or a photo that we just take the video of. So that means what, we had 485 lines, 485 lines. So if 30% line, if 30%, if 30% line we actually miss, so that means what, that 70% of 485 lines, so that is, that is kind of, how to say, 340, I guess 340 lines are, possibly that we are scanning 340 lines out of 525 lines, out of 525 lines. Some lines are missed due to horizontal, vertical retracing, and some lines are missed due to the nature of the scanning. Okay, and this is if we, and this 30% we lose if we do, if we don't do interlacing. If we do interlacing, then the experiment suggests we lose 50%, lines. So you can think of that, actually the real, we actually, scan very less number of lines compared to our ability. Okay, so as I told you that how many samples per line we scan, there is no such standard. It's mostly depends on the, video file formats or the video file standards, right? For examples, if we have video home systems, so this format, then we use 240 samples per line. So that is, so that means, if we have, this is the, if this is our, this is this one line, that means we just collect, the analog voltage, from 240, different, points. So that's what it means. Then we have super, VASs, then we have Betamax, we have standard 8mm, we have high resolutions, that is 8mm. So you see that from 240 samples per line up to 425 samples per line is possible in this analog, formats. Okay, so based on the format that we can imagine that how many lines we have, and based on this how many samples per line we might have, and based on the standard we can determine that how many, lines in every frame we have. Okay, so I'll now, talk a little bit on, frequency perspectives. As we already know that our color, signal or chroma signal is basically the, y or I is, multiplied with, some carrier frequency, and this is cosine, and the Q information, or this is V, or let's say maybe this is Y, right? So these kind of things. So this carrier frequency generally is 3.58 megahertz. This carrier frequency for the color to that I said you, that let's say the color is C equal, maybe U, or let's say I, that is cos 2 pi fc plus V sine 2 pi fc. So this U is also, you can say I, and this V we say Q, right? So this is in NTSC standards, so we say this is I and Q. But whatever, that's not the important things. The important thing is this, the values of this frequency. The values of this frequency F is basically 3.58 megahertz typically. This is for in NTSC. Okay. So and you know that how the composite signals looks like is, the luminous information plus chrominous signals. I already explained, so no need to explain more. So generally the picture carrier, the luminous things, the picture carrier, the carrier frequency for to transmit Y information is basically, you see this 1.25 megahertz, 1.25 megahertz. 1.25 megahertz for picture information to carry the picture. And for color, how much we need? 3 point, as I said you, that is this megahertz is 3.58 megahertz for color carrier. So this color 3.58 megahertz. So that means if we start from, let's say start from zero, let's say start from zero, I mean for a reference point, for a reference, if it is, if I start, some from 0 point, that is at 1.0 frequency, and let's say this is a megahertz. So 1.25 is our carrier, and then 1.25 plus this 3.58, that is 1.25 plus 3.58, this is exactly 4.83. So this 4.83 is basically our color subcarrier, in fact. So this bandwidth we need for our color information. But if it exactly, if picture carrier is 1.25 and if the reference point is 0, so then we have to add this 3.58 with this 1.25, so that is 4.83 for our color subcarrier. Okay. And for any television signal, the video broadcast that we do, we also have the audio signal, right? Now for the audio signals, we need 4.5 megahertz. Okay, 4.5 megahertz for audio bandwidth in is 4.5 megahertz. So that means 1.25 plus 4.5, so that is, I don't know how much it is, 5.75 megahertz. So this will be our audio carrier. You see, that's why this is the audio carrier frequency is 5.75 megahertz. So this is the carrier frequency. And if you look at the communication bandwidth, then you would see that, from exactly this point, from 0 reference frequency to up to, here. So this place, that's exactly in cover picture and color informations. The takes, from up to here. So this is 6 megahertz total channel. There are something others I'm not going to explain. But here, what you need to know is that for video, for in NTSC standards, we are using actually 6 megahertz bandwidth we need. Among that, and you also see that from the picture carrier and from up to here, where the color information ends, so that needs 4.2 megahertz. And for the audio, we need 1.25 megahertz, 4.5 megahertz. And this 1.2 megahertz, if we add up, then the audio carrier is 5.75 megahertz. These sorts of, little bit things you can memorize, or you can just refer this diagram. Okay. Now let me tell you, simple calculations that how we calculate. Generally, 54 to 806, these RF frequency 54 to 806, 806 megahertz, this frequency band we use for television channel. Okay, for television channel, and each channel usually occupied 6 megahertz bandwidth. Now, to calculate the picture carrier, that what frequency will transmit the picture information, what we need to do is, we will add 1.25 megahertz to the lower frequency range, right? So, and how about the sound carrier? The sound carriers, we will add further 4.5 megahertz, you know, to this picture carrier. Let's say we give an example and that will clarify. Let's say, so here you see, let's say channel number, channel number, let's say 2. It is start from, let's say, 54 megahertz to 60 megahertz, because each bandwidth, each channel needs 6 megahertz. Let's say next channel, channel 3 is 60 to 66 megahertz. Channel 4 is 66 to 72 megahertz. And in this way, and for AVF broadcast, this frequency is reserved from 88 to 108 megahertz. Okay, but whatever. Now let's go back. Let's say we will be using, let's say, channel number 6. Now channel number 6 is, if you look at here, the channel number 6 is 82 to 88 megahertz. Now if it is so, then you see, then what is the picture carrier? The picture carrier would be, because this is now the reference point, so 82 plus 1.25, so that is 83.25 megahertz. This is for picture carrier, or for luminance information. That luminance information or luminance signals or the brightness signals will transmit using this carrier. And for audio carrier, what we would do is 83.25 plus further 4.5 megahertz, so that is 87.7 megahertz. Now if I give you any channel, for example channel 6 or channel 5, 4, and if I ask you that what calculate is picture carrier, calculate is sound carrier, you should do it. Okay, now let's talk about that how can we decode the NTSC signal. How to decode NTSC signal. What does it mean, decode? Decode means, we wanted to receive, we wanted to find out the signal that we transmitted. And if you remember, our composite video signal was Y plus C, and that is exactly Y plus, let's say this is the color signal was I cos 2 pi FCT. Let's say it is also better that to use C, so this means C means carrier frequency, okay, plus Q cos 2 pi FCT. Okay, so this is our composite video signal. Now in the receiving end, what we do is you see that how we can receive the signal. First, you see, this is a high frequency, you see FC and FC, right? But here you see there is no frequency here. We can say this frequency is 0. Okay, and this is basically reside in the lower end. So if we use a low pass filter, just let's say we have this one, let's say, and if we pass this signal to a low pass filter, now if what will happen, that if we have this low pass filter, if we use, so definitely we just have this Y information, because low pass filter means low, we will pass the low frequency, we will block the high frequency, and because the picture carrier is in the low the low frequency, so we will obtain the Y. Now if we have this one, when we have the filter, so just when we have the filter, then we just got this one. Okay, now how can we obtain the color information? For the color information is also very simple. You see, this is not difficult, that we understand. Now let's see, if we if we use high pass filter, then we have I cos 2 pi. Will not, I mean, first what we'll do, let's say we have let's say we separate, let's say we have the composite video signal here, composite video signal, and this composite video signal, first we pass through a, let's say, low pass filter. Okay, then we have y. And same composite video signal, what we do, first we multiply with something. Now how do we multiply? So that things, let's say we multiply these signals with let's say 2 cos fct. We'll multiply by this one. Now if we multiply by this one, this is the things that we have this color, and we multiply 2 cos 2 pi fct, then we have I 2 cos square fct, because you already know that this c is, I mean, is better I write here. We already know the c is, that here is, coming is our this composite signal. If this color is 2 cos 2 pi fct, so we'll multiply this by c, and this c is that I cos 2 pi fct plus q sine 2 pi fct. So this is the thing. Now if we multiply these things, we will come up with this kind of expression, that is I plus, you see, I plus I something and q something. And again, you see, this is only I, but here is high frequency term, high frequency term. So what we do, if we again use a low pass filter, then we will filter out this I, and this it will be eliminated. So in this way, we can recover the I information. And how we can obtain the Q information? So same as if we just multiply this color signal, if we multiply it by 2 sine 2 pi fct, then what will happen is, we will have q plus I something and q something. What will happen, you can try q plus something plus something. So this something is basically high frequency. If we again use low pass filter, then we have the q information. So in this way, we can separate I information and q information. And in the beginning, we can separate y information. So from a composite NTSC signal, we can separate by simply multiplying by 2 cos fsct, and again the same way that we can, if we multiply by cos, we can separate I. If we multiply by sine, we can separate q. So that's the thing. Okay, so that is the thing that I already explained. So there are not only NTSC standard, there are also another standard called PAL. PAL standard is called phase alternating line standard. So they have some different mechanisms, and the main difference is that how many frames, how many lines per frame, that kind of, what is their carrier frequency, what is their bandwidth, those are the differences. So also you see, SICM is another standard, so that means the system electronic controller array. So this kind of abbreviation they use. So if we just summarize these whole together, so the TV systems, the analog video information is mainly used for the television. So NTSC TV systems, they use 30 frames per second, or more appropriately 29.97 frames per second, and they have 525 lines in every frame, and the bandwidth reserved is 6 megahertz to transmit all the information. And this 6 megahertz bandwidth, 4.2 megahertz bandwidth is kept for brightness information or picture information. Sometimes this luminous information is actually, we say, picture information. And 1.6 megahertz for I information, and 0.6 megahertz for Q information. For PAL systems, we have 25 frames per second, and 625 lines per frame, and it requires 8 megahertz channel bandwidth. And for video information or picture information, we need 5.5 megahertz, and for color information they use 1.8. For both I and Q component, it is the same bandwidth they use, 1.8 megahertz. And for SECAM standard is this information. So you see, it's all about that what is their frame rate, how many lines, what bandwidth they use, how the bandwidth allocate for picture information and color informations. So these are some comparisons of analog broadcast TV systems. Now we will explain something on digital video. So see, the advantage of digital video is a lot. For example, video can be stored on digital devices, and it is also ready to be processed, that you can remove the noise, you can copy, and you can also incorporate various other kinds of multimedia applications. So digital video is very portable in that sense. And also we can have direct access. For example, if you do the video editing, you can do anywhere you want. Also, if we repeatedly record digital video, so image quality will not be lost compared to analog video. And also the encryption stops, and some sort of other coding decoding things can be done easily in digital video. So that's why the digital video is very attractive. Now when we do the digital video, so we take some advantage of some of the limitations of our you know human eye systems. You see, when we look at the video, if you look at the video now, as I told, the video has two information. One is luminous information and another is chrominance information, right? Or roughly it is color information and this is brightness information. But it's a brightness information. Now when you look at the brightness information, let's say this is our one image or one video, whatever it is. Now we can easily in a very, let's say we just concentrate from just in this place, okay, in this very particular place. Now in this particular very small places, we can differentiate that if there is any differences between the brightness. Okay, if let's say this place, these pixels, brightness information is different from this pixels brightness, then our human eye can easily catch these differences, that this pixel has a different intensity than this pixel. Now very interestingly, you know if this pixel has a different color with this pixel, our eye can't easily determine this. So largely, so that means color information is less sensitive than brightness information to our brain and retina systems. So that's why it is fine that, let's say, I just give you some examples. Let's say here we have, let's say, 4 pixels, you know 1 2 3, let's say this 4 pixels. And let's say the brightness information for these pixels, brightness of this pixel is different from each pixel to another pixel. And so what we do, we can transmit this brightness information for each pixel. But how about the color information? Let's say this one is red color, this pixel, let's say red color. Okay, this is red color. And let's say this pixel is, let's say, blue color. Okay, let's say this pixel is blue color. Now what we can do, maybe I'm just giving an examples. Now how about this pixel, that these pixels, maybe this pixel has some particular color, maybe it might be white color or whatever color. But how about, because this pixel is already red, now how about that if I just keep the same red here, same red here. So what does it mean? I don't care that what is the color of this particular pixel. I'll use the same color because this pixel's color is red. I'll keep this color. I will produce in the reception and wherever, I'll produce the same color in this pixel. So that means I don't need to transmit the information for this pixel, color information for this pixel, because we know that color information is less sensitive for brightness information. So we'll send the brightness information for each pixel, but when comes the color information, I'll keep the color information only for this pixel, not for this pixel. Okay. So similarly, this pixel is blue. So what I can do, I can keep the same blue for the next pixel. I'll just transmit the information for this one, and this one I will not transmit. Rather, I know that because this is blue, so this will automatically be blue. Okay. So this kind of thing. So for some pixels, we will send the transformation, we'll send the information, and for some pixel, will not send the transformation information. So that kind of things we say, chroma subsampling, chroma, chroma subsampling. Okay, chroma subsampling. So this is subsampling. You see, subsampling, we already have the sample data digitally. We already have the digital data, pixel by pixels, right? We have the pixel by pixel data. Now what we are doing, let's say this is all these two-dimensional structures, that. So what I'm doing is we just intentionally we consider, and we allow some of the we just transmit and we just keep the information for some pixel, and for some other pixel we don't care. I mean, I'm talking about the color information. So that's called, we already have this sample data. This is called digital sample data. Now on this sample, we do subsampling only for the color information. That is, if we transmit this pixel information, maybe we will not transmit this one. We'll transmit this one. Maybe we don't need to transmit this one. So it depends on that how many pixels you will transmit information. Sometimes you will transmit, sometimes you will not transmit. So that depends on that what kind of chroma subsampling you use. Okay. And to determine that what kind of scheme or approach, or what kind of chroma subsampling method we are using, so that is determined by some kind of numbers. That is a very interesting numbering schemes. So let me tell you, like that. Maybe that this diagram is a good examples. We always present this chroma subsampling in this manner, that if someone say that, okay, in this video we used this kind of chroma subsampling. Now someone say, no, I have used this kind of chroma subsampling. Someone may say that we have used this kind of chroma subsampling. Now what is this? Let's say what is this. To explain these things, let's say we use first, let's say this one. Okay. Now this first number, this is 4. This means how many samples we are considering, how many samples we are considering together. That is this ABC. This first number A is a number of pixels across we are sampling. Let's say we are considering, let's say, top row. Here I'm just showing 2 lines or 2 row. So how many pixels? Pixel 1, 2, 3, and 4. So this number is 4, is very understandable. Okay. Now the second number, this number is how many of these pixels have their own colors. You see, if we think about that, this first one is red. Now the second one is the red. It means what? It doesn't matter that what is the original color of this pixel. I'm just copying this pixel, right? And similarly, you see this pixel is following the color of this pixel, right? So you can think of this is the original one and this is the being the copied. So in that sense, how many of these pixels have their own chroma? We can say these pixels and these pixels. So 2. So that's why here it is, we have 2. Now the number is the third number. The third number, you see that now we will see that this is the first row that we understand. Now in reference to this first row, that we will see that how many, how many pixels in second row have their own chroma sample. So that means you see here that in reference to the first row, so if you compare these pixels with reference to this pixel, how we see this was red, but this is, this one is red, but this one is blue. So we can say this is, one change happening, right? So that means we are not keeping the same color that we used in the first row. We are now thinking the vertically. The first, this number was, horizontal sampling, and the third number is our vertical, sampling. So when you look at the vertically, so this second this pixel color is different from this one. And you see, we don't care the second pixels because, okay, so we care the second pixel because second pixel is following the first pixel, so we forget this one. Now how about this one? This is red, but compared to this one it was blue, but compared to this blue it was again, you see the red. So this is again another, in a new color. So we can say that how many pixels in second row have their unique color. So we can say pixel 1, and this is another pixel, this pixel 2. So that's why this is 2. Or in another sense, we can say how many vertical changes. You see, from this pixel to this pixel, one change, right? And again from this pixel to this pixel, this is one change. So the 2 changes. So that's why this is 2. So in this way, so let's think about this one. What does it mean? So this 444 means, you see, here are we have how many? We have, 1 2 3 4. So this A is okay. Now how about the second 4? You see, this one is blue and this one is red, this one is blue and this one is red. So that means each one is different. So this red is not following this blue, again this red is not following this blue. So that means we have 4 different colors. And how about this 4? You see that compared to this first row, this is one change. This is again, change because this blue is, but this one is red. Again this was blue, this is red. Again this is red, this is blue. So again, so this is also change. So ultimately, that here we are not doing any, we are not, really, doing any, factorizations. We are, the original and the subsampling is the same. So that's why 444. So 444, it means, you see, the 444, it originally means that no chroma subsampling is used. Okay, but 422, it means, what does it mean? You see, you already imagine, it means that, by a factor of 2, use a by a factor of 2. That means compared to our original, color information, we are now transmitting almost half of the color information. And how about the 420? Now 420 is, it simply means is, you see, again we are doing by factor of 2 in both horizontal and vertical directions. And this 420, subsampling, also some other subsampling method is, mostly used in JPEG and MPEG systems. Okay, so I hope that you understand it. Let's, I give you some other examples also. For examples, that you see this one, let's say this one, why it is 4200. So this 4 means that how many, pixels we are considering. 1 2 3 4 pixels we are considering, and this 2 means, you think about the very first, very first row. In the very first row we have two unique colors, so that means there is 2, you see. And why it is 0? Because compared to the first row there is no change in the second row. You see, this pixel is violet, this pixel is violet, this pixel is violet, this pixel is violet, this pixel is yellow, this pixel is yellow, this pixel is yellow, this pixel is yellow. So compared to the first row there is no change in the second row, so that's why it is 0. So same, if you go here, then you can see, for example, here compared to the first row there is no change in the second row, so that's why it is 0. And this 4, you all understand why it is 2, because you have only 1 pixel and this 2 pixel, there's 2 unique colors, so that's why this is 2. And now you see why it is 2, because it is red and it is blue. Why it is 2? Because compared to the first row this is 1 change, compared to the first row this is the second change, so that's why it is 2. Okay, now let's see that this is our, let's say, our in our original image, let's say the first pixel brightness level is this one, and the second pixel brightness level is this one, the third pixel's brightness level is this one, and the fourth pixel brightness level is this one. And let's say this is our chroma subsampling, we use this kind of chroma information. So that means 444 means we basically don't use any chroma subsampling. So each pixel, we keep the same original, information. Now if we just add up this together, so then it will look like that one. You see the first pixel, it is the yellow, and if you superimpose this brightness information, then we have this one, right? So it means that, let's say the very first pixel is, this is our brightness information and this is our color information. If we just add up this together, it will be look like this one. So similarly, the second pixel is this one, the brightness information, and this is the color information. If you add this together, so we have this one, right? Okay. But if we do, let's say this kind of subsampling, if we do this kind of 422, it means, you know, you see this second pixel following the first pixel, second pixel following the first pixel color. So that is 2. And also vertically is also 2. That is one change, you see, and the second is also change, is second change, right? This is 422. Now the very interesting thing is that if we keep the luminous information same, and if we just take chrominous information like that, and if you just add up these two, it will look like this kind of things. Okay, so this is now changed compared to this one. And similarly, if we use 420, chrominous subsampling, and if we keep the same luminous information, it will look like that one. So this was our original, this is supposed to be original information, it looks like that. But when you use 422 subsampling for chroma, then it looks like that one. And if you use 420 subsampling, it perhaps looks like this one. Okay, so but because it is each pixel by pixels, we don't feel much differentiate. It is also the same. This is y information, this is, let's say, u plus v information, and this looks like y plus v. So there are various kinds of digital video formats standards, that, for example, CCIR standards. If we talk about CCIR, means Consultative Committee for International Radio, and they have different kinds of standard formats. For example, CIF. So CIF means common intermediate format. Common intermediate formats, that's also recommended by ITU, and ITU is International Telecommunication Union. So, and this CIF is basically the same that that we had for analog home video home systems quality. It uses progressive scan, that means no interlacing it uses. And there is also a smaller version that is called QCIF standard. So Now QCIF standard is basically this resolutions is kind of resolutions, the image size is all divided by 8. It is divisible by 8, because this is used for block based coding and decoding, that is highly used in H.261, H.263 that kind of things, and we will you know study that things later on. So if we just have a comparative perspectives, for examples, let's say, CCIR, NTSC standard, CCIR, PAL standard, CIF standard, QCIF standard. So then luminous resolution is, 720, by 480. And whereas, this one is 720 by 576, this one is, 352 by 288. Now what does it mean? 352 by 288, it means this is how many pixels in one line, right? This one means pixels, pixels per line or line width. And this one's means, this is means number of lines, right? Number of lines in one frame, per frame you can say. So CIF is, you see, the smaller resolution. QCIF even much smaller. This has been used basically for low data rate system. And for color subsampling in NTSC they use 422, and for PAL 422. CIF they use 420, and they use 420 subsampling. And how many fields per second? 60 fields per second, 50 per second, 30 per second, 30 per second. Fields per second mean 60 fields per second mean 30 frames per second. And they use interlacing, they use also interlacing, but they use non-interlace or progressive scanning. So either interlace or progressive scanning. Progressive scanning means no interlace. Okay. And this is a example, this is an example that what kind of bit rates we usually require. For examples, if you take these NTS examples that we had, 720, you know how to say, 720 pixels, right, per line. If you think about the 720 pixels per line, and you can think of, there are more other kind of pixels. Then we have total, if you just consider horizontal retracing and those, then you have, let's say, 858 pixels per frame and 525 lines per frame. And this, oh sorry, this 858 pixels per line and 525 lines per frame, 30 frames per second. And for 2 bytes for each pixels, so that is 1 byte for brightness information and 1 byte for color informations. And that 1 byte means 8 bits. So if we just multiply this all together, we see that 216 mbps. So that is typically, if you wanted to transmit, receive the information for NTSC, color information, color video, then you need 216 mbps data rate. Similarly, you can calculate the data rate for CIF, QCIF in the same way. Okay, so ultimately, we now landed with high definition television, right? And high definition television, it's all about that, how many pixels you can consider, how many pixels you can consider in one line. Because if you consider more pixel in every line, that means that is really very highly, that is pixels you are taking care of. and and how many lines you can consider in each frame. Definitely, if you consider more line each frame, it means you're you are really considering that every possible lines you are trying to visualize, you are trying to expose, you are trying to transmit. So if you see, if you If you consider a lot of line, so that means, for each frame your data will be too huge, and that's really very, difficult to transmit. But because the communications bandwidth is increasing and 5G 6G is coming, so now we are able to transmit a lots of high definition information. So it's all about that how many lines you can consider. For example, up to 1080 lines, and in each lines you can have 1920 pixels. So this is really high definitions, and aspect ratio is 16 by 9. That 16 by 9 is aspect ratio, mean that width by height. So this 16 by 9 aspect ratio, that if you have 16 inch in this side, then you have 9 inch in this side. So this is more comfortable for human eyes. And for picture transmissions, you can have interlacing or you can have progressive. So for interlacing, you have 60 interlacings. You have kind of that is 60 frames per second, 30 frames per second, 24 frames per second, likewise. And if even you can have this kind of, that is, you see, 640 pixels per line and 480 lines per frame. And if you really think ultra high definition, super high definitions, for example, you have heard of 4K resolutions. Now 4K resolutions mean you basically consider up to 4000 pixels in each line. And how many lines there are? You see, this kind of lines. There's 2160 lines. Now imagine that you are taking a frame, that in this frame there are, how many pixels you can consider? 3840 pixels, right? And how many lines you are considering? The lines is 2160 lines. Now think of, now if you have a screen, that a photo, and then you have this kind of pixel, this kind of lines, is a true details of information you are transmitting. So that's why this is called 4K or 4000 resolution. So roughly almost around 4000 pixels in each line. Even you might have 8000 resolution, 8K ultra high definition. So roughly 8000 pixels in each line, right? So details. So to handle that, huge information, you really need huge bandwidth. And you can calculate that if this is your, lines per, frame, and then you have 30 frames per second, and you have 38,400 pixels per line, then you can, and 8, maybe 8 bits for your you know luminous information, and 8-bit for your color information. So you need 2 bytes for each pixels. So this many pixels, and you have this many lines, and you have this many frames. So this is your, you can at home you can multiply this all together, and then you can convert to mbps, and you can see that required data rate. So this basically huge communication speed you need. So, and finally, these are some sort of different kind of display interfaces you can look at. For example, this is for component video, this is RCA connector for composite video, and this one is your S video, this is VGA, and this is also some other DVI, this is HDMI, this is DisplayPort. These are different sorts of uh, display interfaces that every day we use. Okay, so this is all about our color, I mean video signals. So, and the next week we'll be starting these things, that is video compression and multimedia frameworks. Especially we like to see FFmpeg programming software for this compression and conversion from one format to another format, and various other kinds of things regarding audio and video. So that will be your programming demonstrations. And next week, so that is as I told you, then October 20, that's on a Wednesday, it would be our midterm exam. and the details will be posted on the Blackboard. So see you next week.